Welcome to the Bridgeport 101 video portion of the class. This is a prerequisite for taking the in-person, so watch the video ahead of time, take the in-person, and then you'll be certified to use both our Bridgeport mill and our Supermax mill. Wanted to cover safety real quick, what's required to work on the mill. You want to wear safety glasses, a short sleeve shirt, long sleeves can get caught in the tooling. So avoid those if you can. Hoodies with strings, neckties, you don't want that hanging down, getting caught in the machinery. If you have long hair, you'll want to tie that back so it doesn't get caught up in the tooling. The mill throws hot chips, so you want to wear long pants, closed-toed shoes. And if you're working on the mill, you do not want to wear work gloves, again, for the same reason. You can get caught in the tooling and pulled in. Thin nitrile gloves are fine. Do get the 0.5 mil. The thinner ones, those will tear away and will not pull you in. So I wanted to cover the parts of the mill itself. The first part we'll cover here is the quill. There's a lock here on the front of it to release it. For the most part, the quill is used for drilling, moving it up and down for drilling. If you are end milling, you'll want that locked so that the quill does not move and the knee is what comes up and down for milling. When you're drilling, do make sure that this is released. The spring should hold it in place and not drop, and with that lever you can move up and down. If the lever's in an awkward place and you're drilling, you can pull out on the handle, readjust the position, and then drill that way. The head itself does have multiple gears. There's a high range and low range. We'll talk about speed adjustment later, but for now, to move from high to low, there's a lever here on the side. You can see right now it's in high. Push in on the handle, rotate it back, that goes to low. Push on the handle again to release it. If, for example, you can't get it into gear, the gears are not synchronized. So if you have trouble getting it into gear, what you need to do is grab a hold of the spindle nose and rotate it and just give it a little bit of a jerk until things go in. Wanted to talk about the parts of the mill. We'll start here on the quill. The quill is mostly used for drilling. The lever here moves it up and down. There is a lock on the front here. If you're end milling, you'll want to have this locked so that it does not move up and down while you're cutting. But for the most part, if you're end milling, you want that locked. And when you're drilling, you do want to make sure that this is released before you drill. There is a spring that holds it in the position, and this lever moves it up and down. If you're drilling and the lever's in an awkward position, you can just grab a hold of the lever, pull out, and it just readjusts it to a more user-friendly position. While we're on this side of the mill, I want to talk about the speed changes. We'll talk later about the speed changes, the variable speed head. But for going from high to low gear, there are two ranges for that. There is a lever here on the side. Right now we're in high. If we flip this lever back, that puts it in low gear. Push that lever in again, comes back to high. Sometimes, like right now, I can't get that. There's a resistance here. I can't get that back to low. The gears are not synchronized, so it's binding up a little bit. So when that happens, what you want to do is grab a hold of the nose of the spindle here and give it a little bit of a turn until you get those gears aligned internally so you can put that back in low. And again, coming back here to high, it's bound up again. I just rotate that spindle and it locks right in. Also, when you're drilling, there's sometimes when you're going to be drilling blind holes that aren't through. There is a stop here on the quill that limits how deep you can go. There is a quick thumb release here. Push on that button, lift that entire thing up, and you can set it quickly. And then you can rotate it to set the depth. There are tick marks on the front of this. Each tick is 1/1000 of an inch. So now if I'm drilling a hole, I come down, I hit that stop. It, prevents me from going all the way through the part. Again, locking the quill. If you're drilling through holes, you just want to get that stop all the way out of the way. So push on the button and pull that all the way down. Wanted to talk about turning the mill on real quick. There is a forward and reverse direction on these, and the reason for that is there's a direction change when you go from high to low gear. The way we have the three-phase wired up in here is forward is the correct direction for high gear. 99% of all cutters are going to want to spin clockwise looking top down. We're in high. I'm going to go to forward here, and if we look at the spindle, that was spinning clockwise for high. If I drop the low again, and if I go forward, you can see that that's turning counterclockwise, so that's the wrong direction for low. Bump it to reverse. We're now going clockwise looking down, so that is the correct direction. Till you get the muscle memory down of the forward reverse versus high-low gear, just bump the power on and see if you're spinning the right direction for the cutter. If you do spin the wrong direction and try to make a cut with that, you're basically going to ruin the cutter. So it's important to get that right the first time. Now jumping over to the Supermax mill, Quill is nearly identical to the Bridgeport. We have a lock here on the front. We still have the Quill handle that raises and lowers the quill. Handle adjustment still works the same. One difference on the quill itself is we do have a digital readout scale that will measure its position up and down. So it makes setting the stop for blind drilling much easier. One difference on the quill stop, there isn't a quick thumb release. So you do have to manually turn that a bunch of times to get it to the correct position. As far as the quill nose itself, we do have this ring light that's around it. So if you need to grab a hold of the nose and rotate it when you're going from high to low gear, you just pull that ring light off. It's held on with a magnet. Now you can see I got access to the nose of the spindle and can rotate it. And this is held on with a magnet. One other difference between the Supermax and the Bridgeport is the power switch itself. If you recall, the Bridgeport had forward and reverse for the direction. Forward was the correct direction for high, reverse was the correct direction for low. Over here on the Supermax, 1 is basically forward, 2 is reverse. So for high gear, you'll want to use 1, and for low gear, you'll want to use 2. Want to talk about the spindle speed changes on the Supermax also. It is different than the Bridgeport. The Bridgeport has a continuously variable speed head. This head is an older style that uses belt changes, much like a drill press. Going from high to low gear on this is a little more involved than the Bridgeport. There's actually 2 levers you need to adjust. There's one here on the side. You can see it's labeled here in permanent marker, high-low. And there's also a lever on the top that you need to rotate, low, high. Both levers need to be in the same position. So if you want to be in high, both need to be in high. If you're in low, both levers need to be in low. If you get them out of sync, I think what actually happens is it stalls the motor. So definitely pay attention to make sure they're both in the same position. So right now we're in high. If we want to go to low, just grab a hold of this, rotate that over to low. Same applies just like the Bridgeport. The gears are not synchronized. This went in smoothly, but if it binds up, remove the ring light, grab a hold of the nose, and rotate that till you can get that in. Also, this lever on the top, you need to rotate around to low. So now we're in, both levers are in the low position. I can bump that over to 2 for the correct direction for low. And now we're spinning. If we want to go back to high, what we need to do is rotate this lever back to high and rotate the top lever back to high also. There is one critical little thing you need to pay attention to when you go back to high. As I rotate this lever over to high, notice how that pulley didn't hardly drop at all. It pretty much stayed in the same position. There's some sort of internal spline in there that needs to drop in and engage. If that doesn't engage, when you turn this back on, it's going to make one heck of a grinding racket. So what you need to do when you go back to high on this machine, pull the ring light off, grab a hold of the nose, give it a quick jerk and rotate, and you watch that pulley drop into position. That's the high-low setting changes. Belt changes. If we look at the front of the machine here, there's a legend here that says, for the different belt positions, what the spindle speed would be. However, I discovered that this chart is wrong. This does not match the picture this picture does not match the physical configuration of the pulleys. So I will eventually make a new legend for this, but basically when you look at this, the speed should be reversed. So if we're in high and we're on the top pulley position, we're not at 2720 RPM, we're actually at 660 RPM. So just flip these numbers in your head, and I know it's odd that this machine looks like this, but that's the way it is. So if we come around to the side, we're on the second pulley from the top. We're in high, so we're at 1115 RPM. If I want to move this belt down a notch to get to a different speed, much like a drill press, you need the motor moves in order to loosen up get enough slack in the belt so you can move that. There's 2 cam levers on this machine to loosen up the motor. This is the slotted side here, so this is the side that'll rotate, but you do need to loosen up this cam lock. If we come around here to the other side of the machine, there's another cam lock here. Rotate that to loosen that up. The best way to rotate this motor to get slack, if you come around here and look at the this motor box enclosure, electrical enclosure, push on that, and what'll happen is you get enough slack in the pulley. So if we come back here and look at the pulleys, I'm going to pull back on this. That tightens it. Pushing forward on that loosens it up. So now I've got enough slack in the belt. It's easier if you move to the smaller pulley first when you change belts. So just kind of rotate it back and forth. Rotate a few times till you're aligned on that pulley. Grab a hold of that motor enclosure again, pull it back, hand tighten it, relock the cam lever on this side, come back over to the other side, and relock that cam lever. And now we've just done a speed change on the Supermax. Moving on to the power feed for the Bridgeport, there is a motor for the power feed. Unfortunately, it does not work on the Bridgeport. What can happen sometimes, though, is that this lever to engage the gearbox gets bumped. And when that happens, if you go to turn it, you kind of feel this grinding noise. Just make sure that the gearbox is engaged in the neutral position so that the X-axis can turn freely. Moving back to the Supermax, the Supermax has the same X-axis that the Bridgeport does, Y-axis, and the Z-axis / knee. As far as the table locks go, it's very similar to this Bridgeport. There are 2 locks here on the front of the Supermax to lock the X. Just rotate those sideways to the right to lock it. To release it, just back them off. The Y-axis table lock is in the same position. Rotate that clockwise to lock it, then release. And there is also a lock on the knee / Z axis. I rarely use it, if ever, but make sure that that's released. When you're using these machines, before you start, do make sure that all the table locks are released. You know, if something's hard to move, you know, stop, take a minute to think about what's going on. Usually if it's the table locks that are the problem. Lastly, on the Supermax, we also have a power feed, which does work on this machine. If you look on the bottom here, there's a toggle switch. That's actually turning it off. If I toggle it to turn it back on, there is a little faint neon light that lines up that tells you that it's on. To move the table, just flip this lever sideways and the table starts moving. This knob here on the front is a speed control. It changes the rate. There is over travel limit switches, so if you just let it go, it'll hit the over travel and the motion will stop automatically in that direction. Flip it back the other way, we're good to go. One other thing to note on the Supermax is besides the knee lock on the front, there are these locks here on the side that'll lock the gibs to keep the knee from moving up and down. Just make sure, you know, if you can't move the knee, that these are also loose. Otherwise, you'll not be able to move the table up and down. Moving on to back to the Bridgeport, I want to talk about the table movement. The back and forth direction on the table is called the X direction. The in and out of the table is called Y. And then the table moving up and down itself is called the Z axis or the knee axis. This works in conjunction with the quill. Like I mentioned earlier, for the most part, you want the quill retracted all the way if you're end milling. You do not want it extended. If you're end milling, there's just a lot more vibration and your surface finish is a lot worse with an extended quill. If you do have a part mounted in here and you're taking a heavy end cut, you can actually turn the ball screw on these. So there are table locks to prevent the table from moving. On the X, on the Bridgeport, there's just one handle here on the front. You rotate this to lock it. Unfortunately, it doesn't work all that great. I am able to overpower it, but still do pay attention to make sure it's released. On the Y-axis lock, if you come around here to this side, there's a handle to lock the Y. Rotate that, and again, it doesn't require a lot of force. And now I'm just feeling the spring back in the ball screw here, but I'm not going to overpower this. But the table is locked in the Y direction now, so just rotate it to loosen it. Moving down, there is a lock on the Z-axis / knee. There used to be a handle sticking out here. Somebody over torqued it and broke it off, so it does not work, which is a good reminder. It doesn't take a lot of force to lock the table locks, so please do not over tighten them. For startup, before you start your work day here on the Bridgeport, we need to do a couple maintenance items. We do need to make sure we get oil to all the ways on the machine. The way that's accomplished is there's a one-shot oiler here on the side. It pushes oil up through these lines to all the ways. On the Bridgeport, you push down on the handle. The lever slowly releases, slowly pushes up oil up to the ways. Just do that once a day before you start your work. The only other daily maintenance item we need to do on the Bridgeport, there's a couple of flip-up cups here that need oil. This lower one oils the spindle. The second one oils the variable speed head. We have the red oil can here labeled whey oil, which is what we use for this. Just grab a hold of that with your finger. It's spring-loaded. Flip that up. Give a few pumps to get the oil primed in there. Get a few drops of oil in there. If it runs out, no big deal. Too much oil means it just runs out the nose. Come around here to the front. Flip that one up. Same deal. Get some oil down in there to get the variable speed head lubricated. And that's it as far as daily maintenance and startup on the Bridgeport. Moving back to the Supermax, the Supermax has the same X-axis that the Bridgeport does, Y-axis, and the Z-axis / knee. As far as the table locks go, it's very similar to this Bridgeport. There are two locks here on the front of the Supermax to lock the X. Just rotate those sideways to the right to lock it. To release it, just back them off. The Y-axis table lock is in the same position. Rotate that clockwise to lock it, then release. And there is also a lock on the knee / Z-axis. I rarely use it, if ever, but make sure that that's released. When you're using these machines, before you start, do make sure that all the table locks are released. If something's hard to move, stop, take a minute to think about what's going on. Usually if it's the table locks that are the problem. Similar to the Bridgeport, the daily startup on the Supermax is we need to get oil to the ways. There's also a one-shot oiler here on the side. Instead of pushing down, you pull out. As you pull out, that's what pushes the oil up. Just like the Supermax, there's a flip-up cup to oil the spindle. There's just one cup here since this does not have the variable speed head. Again, with our red oil can, get a few drops of oil in there, and you're good to go. Wanted to talk about the digital readout or DROs that we have on both these mills. First, we need to talk about the coordinate system. The table itself is actually what moves, and the part moves, but the tool stays stationary. This is true of our mills. This is true of CNC machines. The frame of reference is you always think of the part as staying stationary and the tool moving around you. So if we look at this part we have in here right now, the coordinate system is x-axis is to the right for positive x, negative x is to the left, positive y is away from you to the back of the machine, and negative y is towards you to the front of the machine. So if we look at our tool here, look at the DRO at the same time, even though the table here is moving to the left, your frame of reference is the tool is moving to the right, which is in the positive x direction, and you can see our x-axis is increasing. Going the other way, the tool is moving, quote unquote, in the negative direction here, and our x-axis on the DRO is also moving in the negative direction. We come back to center. Here the tool is moving towards the back of the machine, which is in the positive y direction. Y is increasing, coming back the other way. The tool is moving in the negative direction, and y is getting more negative. The same applies for the z-axis. In this instance, the table is moving up, but from the reference of the part, the tool is moving down, which means the z-axis is decreasing. Here, the tool is moving up and away from the part, which means z-axis is increasing. So that's the frame of reference for the coordinate system. Actually using the DRO, we'll get into edge finding here in a little bit, but if you want to zero out, let's say your x-axis, there's a dedicated button on the Supermax machine. You hit the x0, that zeroes out the x-axis. When you get into edge finding, you need to take into consideration the radius of the edge finder itself. So instead of zeroing the axis, you might actually want to enter position. So instead of hitting X0, you hit the X button, and then if it's negative 0.1 is the radius of your edge finder, and then hit enter. So you've actually entered a position instead of zeroed it in that case. Also want to talk about incremental versus absolute mode. For the most part, you'll want to stay in absolute mode. So I think of incremental and absolute as absolute is your golden original frame of reference which you edge found on. Incremental is kind of a secondary reference on top of absolute. So this can come in handy. This example, the math is easy, so it's not, you could do the math in your head, but let's say you were drilling 3 holes that were 1 inch apart, but the first one is 2 inches from the edge. So you zero out your part. You move over the 2 inches to drill your first hole. I'm going to kind of round here and just get close and not be precise. But so if we jump over, we're in absolute mode, we move to 2 inches, we jump over to incremental mode, and we zero out there, drill our hole, move over 1 inch to drill our second hole, zero out here in incremental mode, drill our second hole, move over 1 more inch, zero out, drill our third hole. So we've moved 2 inches plus 1 inch for each of the second and the third hole. So we've actually moved 4 inches from our edge. If we jump back to absolute mode, there's our 4 inches. So it's kind of a second reference system on top of your absolute. So it's nice for doing relative moves instead of, indexing from your 0, 0 datum. Another nice feature of this machine is if instead of edge finding, you want to center find. So let's say you come to one edge of your part, let's say you find the left edge of the part, zero that out, come over to the right edge, let's say it was about 3 inches or so, instead of doing the math, this thing will do the math for you. So if you hit X 1/2 divided by 2, it took that right edge divided by 2, so now we're at 1.5 inches, which is the right edge. And if we move to 0, that should be the center of the part. So it's a nice feature of this DRO. Since the Bridgeport DRO does not have a scale on the Z-axis, you will have to use the dials for that. Each tick mark on this dial, and you can see up top here, that's the indicator mark. So each tick mark is 1/1000th of an inch. One complete rev of the handle is 0.1 inches. And you can see right now, this is actually freewheeling and not moving with the handle. So what you do, once you touch off on your part, rotate it around to 0, get 0 lined up, lock this second nut down. So now when I turn the handle, this turns, the dial turns with the handle. So we've gone around one complete rev here, back to 0, so that was 0.1 inches. Moving clockwise raises the table, moves the table up, which is actually moving, quote unquote, the tool in the negative direction. To raise the tool, basically you move in the counterclockwise direction. On the Bridgeport Mill DRO, we only have scales on X and Y. There is not one on the Z-axis or knee. So if you're using this machine for vertical height changes, you'll have to use the dials. But as far as the X and Y axis go, a little bit different operation here on zeroing and entering numbers. If you went to 0 axis, you actually hit this 0 button twice. That zeroes the axis. If you want to enter a position, like we did on the Supermax, the radius of our edge finder, you hit 0 once, type in the number, 0.1, minus 0.1, enter, and that's how you enter position. So it's the same button here, where on Supermax there were different buttons. Here on this Bridgeport, hit 0 twice is actually 0, hit 0 once to enter position. Both of these DROs you can change from millimeters to inches on the fly. Just hit that button and you can switch back and forth. It's handy, especially if your edge finder, it's 0.2 inches in diameter. You can edge find in inches, get your 0, established, and then switch over to millimeters if that's what your part is dimensioned in the units you're working in. Wanted to talk about the head adjustments on the Bridgeport, and the same applies to the Supermax. At one point in the life of this machine, this table was precision ground flat. It's been dinged up a few times. But when you're milling, the goal is to have this nose perfectly parallel the table, so that when you make cuts, end cuts, face cuts, they're flat, perpendicular to the surface of the table. The vise sits on top of the table. It's precision ground flat. All these surfaces are parallel to the table. So the goal is to have the nose parallel to the table and to the vise. The head is adjustable. There are situations where, you can make an angled cut. If you had a short enough piece, you could mount it in the vise sideways to make an angled cut. But if it was too long, you would actually have to tilt the head with the piece flat in here in order to make an angled cut. So I'm going to mention this just so you're aware of it. There's 3 bolts here and a worm drive that allow the head to tilt this way, which is what we call the nod, kind of the forward and up and down motion. If you look here on the front, there's also 4 more bolts and a worm drive to adjust the tilt back and forth. So if those are not perfectly in alignment, if you were to, for example, if the nod was out, if you were to make overlapping cuts with like a 1/2 inch end mill on the face of a piece, those overlapping cuts would make like a sawtooth pattern. So it's one thing to be aware of. When I come in here to machine, I never check the alignment of it. I assume it's correct, but just be aware it could be off, when you're making your parts. For the most part, don't adjust the head alignment. If you think it's out, please contact the shop captain. Let us know, we'll check it. If you do have a part that you need to make compound coping cuts on, let us know, and we'll demonstrate how to actually, uh, you know, change the alignment of the head, set an angle, and then bring it back for the next person. Next, I want to cover the clamping methods, work holding methods on the mills. 90%, 99% of what people are going to do in here, we're going to use the machinist vise. What we have on here is a set of aluminum jaws that are what I call accidentally sacrificial jaws. You know, if you do make contact, you know, damage the vice jaw is not your tool. However, you know, there are instances where you've got a small part or something where it's just difficult to hold and you do need to cut into the jaws. Please do not do that with these jaws. Make your own, make a sacrificial jig, whatever. You can see here there's a couple ding marks in the jaw faces where people held screws in here to probably machine a flat on the top of them. That's perfectly acceptable to do on this machine, but please just real quickly grab a piece of scrap aluminum so that scrap aluminum is what gets marred and not these aluminum jaw faces. Let's try to keep these in as good a condition as we can for the next user. If you do have some work that's you need more precision out of, we do have precision ground steel jaws that reside on the shelves over on the other end of the workshop. You're welcome to put these jaws on the vise. They're just held on with socket head screws on both sides. I just ask that when you're done, take the steel jaws off, put those away, and put the aluminum soft jaws back on. For the most part, a lot of your work will be held between the jaws here. I think these jaws open up to something like 6 inches. However, if you've got an 8-inch piece, you can still clamp it in this vise. One thing you can do is, for example, move the jaws, either one or both, to the back sides of this. Now you've got, you know, basically essentially a 12-inch jaw opening here to clamp wide pieces. The only problem with that now is you're not in the space between the jaws, you're on top of the jaws itself, so you do have to be careful about through operations and not damaging the vise itself. But that's one other method to clamp wider stuff, you know, in the vise itself. Another method, if you've got a odd shaped piece that, you know, just it's not square, you don't have any flat edges, you can't get it in the vise, you can clamp directly to the table itself. We do have clamping kits over on the white cabinet that you can use. Just a real quick demo how that works. You have a T-nut with a stud that goes in the T-slot. You have your part here. We have these interlocking angled stair steps that allow you to adjust different heights. So this kind of supports the back side. You get it to the right height and you just screw the nut on, and that tightens down and pushes the force down on your part that would be underneath here. The problem with that is all your force is in the downward direction. You have no lateral side support, so you do have to be careful about how aggressive a cut you take. You can, you know, parts can slide out from underneath these clamping kits. Same applies to working on top of the jaws of the vise. You do have to be careful about through operations when you clamp directly to the table. So if you're doing through operations, put spacers underneath it before you clamp to the table. Other work holding options we have here in the shop, we have a rotary table. I don't really cover it in this class, but I just wanted to mention it. This basically will bolt down to the table. You can clamp round parts in here, so you have a rotary axis to do slots. You can even clamp square parts in here. You can do larger diameter holes with this rotary table. You can also rotate it up on end, so the rotary axis is in this particular direction and allows you to mill flats on, you know, round pieces. You know, you could do odd stuff like make 5-sided bolt heads and things like that. So those are the basics of the work holding that we have available here in the shop. One other handy tool we have here in the shop for work holding in the machinist vise on the mill is we have these collet blocks, which are really handy for holding round stock. So if you grab a 5C collet from the lathe, these are all in 64th inch increments. They're meant to hold round stock, unlike the R8 collet here on the machine, which holds tooling. So you size the collet for the round part you have. You can put it in this collet block. There's a nut on the back side. I'm not going to tighten this all the way down, but screw that together, tighten that down, that'll hold that stock. And now you can clamp that into the vise itself. You can, put a flat on it, do a slot, rotate it around. Besides the square one, we also have a hex collet block. So if you had a round shaft or something you wanted to put a hex head on, you could clamp that in this collet block, mill a flat on it, rotate it around, mill another flat, do that 6 times, and then now you've milled a hex head in a piece of round stock. So the collet blocks are another option you have. These reside over in the white cabinet over on the wall over there in one of those drawers. Earlier in the class, we already talked about the head adjustment and the goal of getting the spindle perfectly parallel to the table. The next step here in setting up, getting ready to make your part, is making sure that this vise face is perfectly parallel to the axis of motion of the x-axis. So that's called indicating or tramming the vise. The tool we use for that is a dial test indicator. It's a little bit different than the plunge style indicator that has like an inch range of motion that you're used to. These work on a lever basis. You can see there's a little bit of range of motion there. This lever is just kind of held in with friction, so you can kind of set it at whatever angle you want. But within the range of motion, there's only plus or minus 1.5 revs of motion, so it has a very limited range. So when you're using it, you want to make sure you don't extend and bottom this out in one direction or the other. When you're using it, I suggest maybe just going half of a rev, and then when you're running across your vise face, you've got enough play in there left that you're not going to bottom it out. The way we use this, this comes up and mounts over the nose of the spindle. There's just a thumb screw on the back to hold it in place. There's about 10 different degrees of motion in this thing, but just make sure everything's tight. And what you want to do is run that needle across the face of your fixed jaw here. So if we bring that forward, it makes contact. And if we look at the actual dial itself, I'll back off here a little bit, come forward. There's the half a rev I was talking about. So now, if we run this table back and forth, we can see the needle moving. And the absolute value of that doesn't matter. This is just relative. So our needle's in contact with the jaw face. And if you watch the dial up here at front, you can see that as we move from right to left across here, that dial is decreasing in value. So what does that mean? So if I back off, I come forward, as I make contact with the needle, it's growing. So that means that growing means that the jaw face is getting closer to me. So as I'm going right here, the needle's growing. What that means is that this jaw face is closer to me than the left side. So what we need to do is skew the vise this direction in order to get that in alignment. And a technique to save you a whole bunch of iterations is start at one end. We're about at 0 right now. Move all the way to the left end, which is 10. Yeah, we moved about 15 thousandths. So each tick mark on here is half of a thou, 0.0005 inches, and we move 15 thousandths. So a technique to kind of iterate faster is move from one end to the other and take half of it out. And like I said, this jaw face is closer, this is further away, we need to skew this way. So if we tap on this end and we take half of that out, so if I move down to about 7 there on the dial, and now if I run it back and forth, you can see we're hitting divots and the damage to the jaw face, but this is kind of a rarity. On the first try, I got it pretty close. We're maybe a thou out here. We're still growing, so I overshot just slightly there. So if I bump it back, and again, I mean, this is a thou over 6 inches, so I mean, this is not much at all that we're dealing with here. So, and actually, if you know, this jaw was machined on the MyTech over there, so it's not perfectly flat. You can actually see the bow in the jaw face itself once you get it dialed in. So I'm going to call that good. You can, when you tighten the vise down, if you start cranking on it, you can twist it back out. So what I do is gingerly go back and forth from one side to the other, not cranking down real tight on one side or the other. Just kind of back and forth until I get it tight. And then one last time, run it back and forth to make sure I didn't tweak it out. Yeah, I mean, we're right on there. So that's how you tram the vise. When you're done, just take it back off and return it to the cart here between the mills. Sometimes you will find this over on top of the lathes if people were using it to dial in a part over there, but for the most part, this is its home. Next, we're going to cover mounting the part in the machinist vise. For smaller parts, you're almost definitely going to need parallels, which reside in this box here on the cart. Parallels are precision ground steel. They're matched height. And the goal of what those do is, you know, if you had a large part, you would just set it down on the bottom of the vise here. Well, we can't really put this part down on the bottom because we can't, we hit our jaws if we were going to face mill. So we want to lift it up, but maintain parallelism to the precision surface of the vise. So what we do is we set a couple parallels in here, grab our handle, crank this down to get it closer to our width of our part. And if you look here, the goal here is to leave the part above the jaw surface so we can face mill this without hitting our jaws itself. You know, there's only an 1/8 inch lip there to grab a hold of, which is plenty for a part this small. You really don't need a whole lot. You know, if we were going to face mill this and end mill this in one clamping setup, we can, you know, leave the part hang out the right side so that when we come in with the end mill, we're not going to hit our jaws again. One thing to keep in mind is you need to make sure that, you know, there's no chips in here. Cleanliness is key. If you have a aluminum chip holding your jaws up, you're not going to be parallel on one side or the other. So just make sure things are clean. Get the part in there. Clamp down a little bit. Just make sure your parallels are against your jaw faces. Clamp down. This is the fixed jaw of the vise. This is the movable jaw of the vise. What happens is this has a tendency to lift as you clamp down. So once you got it mostly tight, just take your dead blow, give it a whack, push the part down on the parallels. So that one's still a little bit loose. So my parallels are tight now. I can't move them. When I crank this handle down even further, that lifting action loosens up those parallels. So again, this is just a precision thing. If you need to be tight on your parallels to make sure that, you know, your part is perfectly parallel. So as you tighten it up, you might have to give it a couple whacks to get it back down on the parallels, and those are tight again. So that's mounting the part in the jaw of the vise using parallels. Wanted to talk about the R8 collet system, which both the Supermax and the Bridgeport use. The way this collet system works, there's a draw bar that goes down through the center of the spindle. I've just pulled this out for demonstration purposes. You would not normally need to remove this. But this bar rests up on a flange up in there, goes through the center of the spindle. The collet goes up in the spindle nose, and this screws in the back of that and pulls this collet up. I'm going to put this back briefly just to show you where it resides. That drawbar dropped all the way down in there, that's because the spindle, the quill is not retracted. To get access to the top of the drawbar, the quill does need to be retracted, and now we see we can get a hold of that hex head on top of the drawbar. So the collet itself is tapered. The inside of this nose is tapered. There's a key slot in the side of this collet. There's a set screw internal that spindle, so when you put the collet in, you have to rotate it to find that key before it'll go up in there. And the way it clamps around the tool is that taper, the collet split. The tool itself, there's this weld and flat, which doesn't apply here to R8 collets. It's meant for set screw type tooling, which this is not. But when you put a tool in, make sure the weld and flat's up in there. The flutes are exposed. You don't want the flutes up inside the collet. You want to have as minimal stick out as you can. The longer the tool, the more vibration and chatter you get. So just the minimal amount of stick out. When the collet goes up in, rotate again to find the key. Reach up on top, hand tighten the drawbar in the back of the collet. And you can see here as I continue to tighten, that collet is getting drawn up into that taper. Insert your tooling, and you almost need 3 hands to do this at times, but get that as finger tight as you can so that the tool does not drop out. And I actually like to be over the mat so that if the tooling does drop, it hits the mat and not the steel. We're held in by hand. Grab the wrench, which we usually, people put it back here on this worm drive bolt. When you go to tighten the drawbar, you come around here to the front, we have a brake to hold the spindle. Just for you people that don't have experience, just be careful. The brake and the power switch are really close together. Till you get the muscle memory down, make sure you're grabbing the right one. I mention that because I've seen students grab the wrong one before, and if you get your hand up there, it's going to rip the wrench right out of your hand. So do be cognizant of that. To break it, just push forward on this lever. That'll hold the spindle from spinning. Come around here, put the wrench up on the drawbar, pull the wrench towards you, going clockwise, just like any right-handed thread to tighten it. It doesn't require this to be super tight. If you over tighten it, you make it difficult to get back off because the brake will slip. But once it's tight, your tool's in there, you're ready to cut. So you're done milling, it's time to remove the tool. And this is the part where you almost need 3 hands. Break it. Again, make sure the quill's retracted so you can get access to the drawbar. Put the wrench on top, and you want to loosen it just to the point where you can do it by hand. If you keep going, the tool could fall out, but many times what happens is, so I've gone a couple revs now, and I cannot pull that tool out. It's because that taper is wedged up in there. So what you want to do is just back off 2 revolutions on the drawbar. You want the threads of that drawbar still engaged in that back of that collet. You want multiple threads. You just don't want one thread engaged, because what we're going to do is whack the top of this to break that taper. And if you've got a single thread engaged, you could either damage the collet or damage the drawbar. So we've backed off our 2 revs, grab a hold of the tool. With the wrench, some people use a dead blow hammer. This is just quicker because the wrench is here. Give it a whack, and that was enough room there to break that taper so that that tool would come out. So now you can loosen by hand and take that collet out. Wanted to talk about tooling here in the shop. For the most part, we recommend that people buy their own tooling. We do have some tooling available here on the cart. The end mills are generally in poor condition. We do have some useful tools for the community. Edge Finder, which we'll get into a little bit later, is usually available here in this wood block. There's a few center drills. Let's see, maybe that one end is good, that one's broke. Tap followers. But for the most part, when it comes to end mills and drill bits and things like that, users should really buy their own. Speaking of end mills, you can get high-speed steel end mills, you can get carbide end mills. For the most part, if you're working aluminum or mild steel, don't waste your money on carbide. High-speed steel is more than adequate for softer materials like that. Carbide wants to run at a higher RPM, which these mills can't really support. They're more brittle. High-speed steel is cheaper, and for, like I said, for aluminum steel, does the job adequately. In high-speed steel, you'll notice that there's typically 2-flute and 4-flute end mills. The advantages of 4-flute is that the core is stronger with the more flutes. You can see that with a 2-flute, the core is thinner. For the most part, 4-flute is better for steel. You get more cutters flying by at a given RPM. For aluminum, 2-flute is better. The reason for aluminum is there's a phenomenon called chip weldment that can happen with aluminum. If the chips don't get cleared fast enough, they can get hot enough, they kind of, for lack of a better term, to get sticky and can actually stick to the cutter edge, which is where the term chip weldment comes from. And when that condition occurs, you no longer have a cutter and you're probably going to break your tool or rip the part out of the vise. 2-flute allows for more chip clearance. If you're doing pockets, internal pockets, 2-flute is better. Both 2-flute and 4-flute will cut aluminum and steel just fine. Just beware of, the limitations of, the materials and whether you're cutting internal pockets or outer edges. I wanted to briefly mention climb cutting versus conventional cutting in this video. We'll put a link in the video to a document that describes in detail the mechanics of the differences between the two. But for the purpose of this video, what you need to know about climb versus conventional. Climb cutting does leave a better surface finish. So if I'm milling a piece down to size, I might plan for a climb cut to be my finishing pass. I might alternate between climb and conventional as I'm roughing out a part. The other issue with climb cutting is in softer materials like copper and even brass, it has a tendency to grab. So you want to avoid heavy climb cuts if you're working in materials like copper and brass. I wanted to cover technique for edge finding. This is valuable, gives you a lot of precision in the parts you're making. Find the edges, you can use it to find center, set our DRO position so that we get an accurate 0-0 datum on this part. The edge finder itself does not like to run at high RPM, so we'll start the spindle up. In the case of the Supermax, I've already set this down to 1115 RPM, and generally you want to be 1000 RPM or maybe even slower. They don't like to run at high speed. The technique for edge finding is we'll start this up. You can see initially we've got a lot of wobble in that. We'll come into our part, raise the knee up to get closer so that edge finder can find the edge. As we come in and start to make contact with the part, that starts to get really concentric. I'm just going to demonstrate the wobble again. That part gets really concentric. And when it hits the edge, it jumps off. So it jumps off sideways. So right there, that's our edge. I'm just going to stop this so we can kind of talk over this a little bit. If we come around here to the front and look, what we want to do is define the spindle centered right over that edge. But you can see our spindle's off of the edge by half the diameter of the tip of that edge finder. So the diameter of this is 0.2 inches. So we're actually 0.1 inches off of our edge right now. So we need to compensate for that when we set this. And again, if we reference back to our coordinate system, we are actually on the negative side of the part right now in the negative x direction. So our current position is negative 0.1, half of that diameter. So if we come over here to our DRO, remember to set a position, you hit the X button, negative 0.1, enter. We've just set our position to negative 0.1. And to verify you got the positive negative right, as you move off of the part, you should be moving away from 0. If you move through 0, you had the positive negative wrong. And just as one more sanity check, if we raise up our edge finder and actually move to 0, close enough there. If you sight down the edge here, the center of our spindle is now lined up with our edge. So we've defined this left edge here is our 0 position. So now, as we move across the part, if we say we had a tool in here, we can precisely, accurately locate our tool at a given position with our DRO. We just covered the edge finder. Wanted to briefly cover center finder. This particular tool has both an edge finder on one end and a center finder on the other end. The way you would use a center finder to find the center of the hole, you would lower the center finder down into the hole in the combination, moving the X, Y, and Z axis to keep lowering it until basically that conical tip is centered in the hole and the wobble part is perfectly aligned with the shaft, and that basically means you found the center of that hole. Wanted to cover tapping. We'll get more into detail this on the hands-on portion, but just wanted to describe a technique for hand tapping on the mills. For those of you that tapped before, you're probably very aware how easily it is to break a tap. Taps are quite brittle. If you get off axis at all while you're hand tapping, it's easy to snap these. So one thing we can do on the mill is use what's called a tap follower. There's a taper typically in the back of hand taps here. This tap follower has a conical shape and is spring loaded. So as you bring that down and that spring compresses, if you put this up in the chuck, bring that down, you keep this all coaxial so that as you're hand tapping, it's hard to get off axis. You can use a chuck or put it up in a collet if you wish. Not generally, you do not want to put mills in a drill chuck. They're not meant to handle side loads, meant to vertical only. So drill bits only. We're not going to turn the machine on, and we're not really applying the lateral load per se, so it's okay to put this in the drill chuck. Over center of your hole, bring the tap in. What I do is bring the quill down, compress that halfway, lock the quill, and usually you will want oil for this. We have these blue dipping pots scattered throughout the shop. These are just filled with mineral oil. Just apply a little bit of oil here to the tap. And then as you tap, typically go 2-3 turns forward. You'll get some resistance. And then what I do is back off. And typically you'll feel like a little resistance there as you come an eighth, quarter of a turn. You just have to, basically there's a chip that needs broken off. Back off. Go forward a couple more turns until you feel resistance. Back off, and just repeat and rinse. One thing about these hand taps there's about 12 threads of taper on them. So this is 3/8 of an inch thick material. To cut all the way, to get those threads fully cut, you almost have to take this top thread all the way to the bottom because of the taper. So a lot of times, the other thing about these hand taps, the flutes are really shallow. There's not much room in there, clearance for chips. It's easy for it to get gummed up and get packed with chips, and especially in aluminum, you can gall your threads as you're cutting it. So a lot of times I'll back off and take a chip brush and try to get some of those chips cleared out before I move forward with my next tap. You can see right here I've come off of the spring tap follower a little bit, so I'll lower my quill a little bit, and then I'll just keep going until I'm done. Once you've cut all the way through, at that point it's probably safe to back this out. You're probably not going to break the tap at that point, and then just unscrew it. And you've got your threads cut. So finally, when you're done with your workday, cleanup is very important to us here in the shop. Our TinkerMill motto is leave it cleaner than you found it. As far as mill cleanup goes, you can take a chip brush, make sure you get most of the chips out of the vise. This mat back here that protects the ways. A lot of times I'll just take a chip brush, brush it on the floor. If you make a lot of chips, you'll have chips down in the T-slots. Make sure you get in there, clean that out. Any collets, drill chucks that you had in there, make sure you remove those. Parallels, take those off, wipe them down, put them back in the red box. We also have a shop back here in the shop. This particular one, the switch is broke, so as soon as you plug it in, it turns on. Only plug the shop vac into the wall outlets. Do not plug it into any of the machine outlets. Those are only rated for 2 to 3 amps and meant for like DRO, low current things. You'll blow the fuse or pop the circuit breaker if you plug the shop vac in there. We do have dustpans and brooms on the side of the white cabinet on the wall over there. Both sides, there's a brush here on one side and a dustpan and broom on the other. Lastly, make sure that you get all the chips off the floor. Chips do get thrown wide, so sweep a little wider than you think you need to. As far as the chips that end up on the base of the mills themselves, they're covered in oil. Don't worry about cleaning it up. We occasionally have to come in with a absorb mat and clean that mess up, so don't worry about that. We do have a compressed air hose here in the shop. You can use, generally use this sparingly for cleanup on the mills. I would prefer you use chip brushes and things like that or the shop vac. We don't want to get chips blown into the ways, but sometimes if you've got, especially if you're tapping, blowing air down into the hole to clear out oil and chips is fine. But as general cleanup, air just blows chips everywhere, so avoid that if you can.